Okay, let's have a look at proving the following. So it's the proof for the probability of a complementary event. So that the probability of A's complement is equal to 1 minus the probability of A. But this proof can also be interpreted to be that the probability of A is equal to 1 minus the probability of its complement. So proving that either of these are true would imply that the other one is also true, because it's just basic algebra of shuffling the order around. So we'll just look at proving the statement in general. For this, we'll need a few axioms. The axiom we'll need first is that A's union with its complement is equal to the space, or sometimes denoted with an S. Some countries use omega, some textbooks use omega, some textbooks use S. It's the same thing. So we'll be using this axiom. The second axiom we need to know is that A's intersection with its complement is equal to the empty set. And from this, we can see that A and its complement are mutually exclusive. There's no elements in A that are also in its complement, because the intersection between A and its complement is an empty set. Okay, so for the proof, we'll start by using the first axiom and saying that let A be a non-empty set. The reason for this is just so that there's no loopholes that we can accidentally create within the proof. So we just say let A be a non-empty set, so when you take the intersection with itself, you will get the empty set. So let A be a non-empty set. Then from here, we can say that A's union with its complement is equal to omega. And thus, the probability of A's union with its complement must be equal to the probability of omega. And the axiom that most people should know is that the probability of omega, or the probability of the whole space, is 1. So we can then deduce that this is equal to 1. So the probability of A union with its complement is equal to 1. Then when we work out a union like this, it is equal to the probability of event A plus the probability of its complement, and then we know this is now equal to 1, right? And we can do this because A and A's complement is mutually exclusive, right? That's why we can do this addition rule. You'll see in the proof that I did for the probability of the empty set, showing that something is mutually exclusive is very important, but you can see it from this. Whenever a set's intersection with another set is an empty set, you know they're mutually exclusive because they don't share any elements. And from there, we can use this addition rule. And now it's just as simple as making the order to be the probability of A's complement equals to 1 minus the probability of A. And that is the proof for showing that the complementary event is just equal to 1 minus the probability of the event.